Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to introduce Guy Blalock from Carnegie Mellon. Guy has been doing parallel computing, parallel programming languages for a long time, at least as long as I've been in the field. And he's told me that he never gave it up, even when the rest of us went off and did something different for a decade or so. He kept on, working on it as at least a sideline. And so it's back. We're fortunate that he's back, and he's going to tell us about some work on parallel thinking. Guy.
Okay. Is the microphone on? Can you hear me?
Yes.
Okay. Yeah, so this is actually, parallel thinking is actually part of a Microsoft-sponsored Center for Computational Thinking. You might not know what this is, but actually Microsoft gave Carnegie Mellon some money back when Jeanette was department head. She was very interested in this notion of computational thinking, which I'll describe in a moment. But now Jeanette's actually gone off to head up SCIES at NSF, and she's actually been putting a lot of these ideas from computational thinking into SCIES, and so a lot of the call for proposals and stuff coming out of NSF have that term in it, computational thinking. So let me just give the background. What is computational thinking? Well, Jeanette's idea was that there's a lot of sort of core foundational ideas in computer science in the way that we think, which are different from the way that people think in other fields, in other sciences. And that it's sort of important to identify what those ideas are for a few reasons. So these ideas are things like abstraction, that we somehow use abstraction more than in most other fields. So we develop our own abstractions all the time, whether it be the interface for a data structure or whatever. We're developing them all the time, and they're really a core part of the way that we think in computer science. Another one is recursion. So this is an idea that's completely embedded in us. We don't even think twice about it. But in a lot of other fields, when you first see recursion, it's sort of baffling. There's various other ones like the idea of reductions, that you can prove a problem hard by reducing one problem to the other. Anyway, there's lots of sort of core ideas in computer science. And the reason it's important to understand them is, one, it's sort of an educational thing. Is to develop curricula, you want to understand what the core ideas are so that you can emphasize those in your courses. And a lot of the motivation for this came out of a general feeling about 5-10 years ago, and not just at Carnegie Mellon, a lot of places that are sort of what we were teaching, especially in high schools, but also in intro courses in colleges, was emphasizing sort of Java programming or some low-level hacking of some kind, instead of emphasizing what the core ideas of computer science are. Another aspect of it is just a PR thing, which is we should really make it clear to people outside of computer science that computer science is not, again, Java programming. It is, some deep ideas, and it's real science. And what are the ideas in that real science? What is the science behind computer science, right? And that's what computational thinking is. The third aspect is this thought that maybe you can take the way that we think about problems and apply it to other areas and actually get innovations by doing that. And in fact, I think Christos Papadimitriou at Berkeley calls this sort of the computational lens. So if you look at certain problems via a computational lens, whether it be a problem in economics, a problem in physics, or whatever, you might have a different way of looking at that problem and therefore actually get a better way of approaching it. So anyway, that's what computational thinking is, and Microsoft was generous and gave some money for that. And this project I was doing actually came out of that on parallel thinking. And so the idea, obviously, is that there's some core ideas in thinking about parallel programming and develop parallel codes. And the question is what those core ideas are and why they might be useful. Okay, you've all seen charts like this, I'm sure. This particular one, many of you have probably seen this exact one, is from Andrew Chen at Intel. It's showing the increase in cores over time. I guess we're at 2009 now. Nowadays when you buy a multi-core, it's either got 4 or 6 cores, or some of them have 8. In a few years, we're going to have 12 through 32. And I guess the most interesting point here is that 2015 is not that far away. It's 6 years away. And at least Intel is predicting that you'll have 100 cores on every chip on a laptop you buy. Okay. I'm not sure how precise they're trying to be. They're sort of nebulous where it's placed. But that's the idea. So the question is, how are we going to use all these cores and what are we going to do with them? And what are some of the problems in moving into a world where instead of a single core we have multiple cores? Well, one is building the hardware. I actually think this is the easiest to deal with, and Intel's just going to do it for us, or various chip manufacturers. Exactly what it's going to look like, I think, still has to be worked out. And I haven't signed the appropriate non-disclosures, so I can't say what the next generation will look like. But that's moving ahead. Then there's developing good programming language and parallel extensions. I think there's a lot of efforts nowadays to do this. So there's some very nice work. I don't know whether it be like Silk++ and various other language extensions. I think it'll be a while before these play out. I think there'll be several OpenMP, et cetera, out there, and some of them will work better than others. Developing good compilers, runtime systems, and debuggers. I think developing good debuggers is actually a very interesting field. Developing good OS support. Then, of course, there's just the fact that a lot of companies have a huge code base. I don't know how many lines of code Microsoft has, but I assume it's very large. And even if only a small fraction of it needs to be changed to deal with multi-core, right? Because we can't just, as in the past, just rely on the frequencies speeding up. We actually now have to make use of those multiple cores. Then clearly there'd be a huge amount of work here, which then ties into this notion, which I actually think is the hardest part of this all. The most likely thing that's going to create a failure here is not any of these technologies. I think a lot of good ideas were developed over the last 20 years in all of these areas. I think the biggest problem right now is that most people out there, people that we've graduated, know almost nothing about parallelism. Okay? And part of this is that I know certainly at Carnegie Mellon, we haven't been teaching parallelism for many years. And only recently we've started teaching some courses on parallelism. So all the students we've educated in the last 10 years know very little about parallelism. And this is changing, but this is going to take a while. And if you don't have people who understand parallelism, then it's going to be a problem because they're not going to be able to use these things, or these things won't be designed very well because the people who are coding them or writing the compilers maybe don't fully understand. So I think there's a real issue here in getting people to understand all the issues of parallelism. A lot of these things are things that as a community we understand, but we haven't educated our students and our workforce. So what I want to do is sort of take an approach to parallel thinking that's similar to the idea of computational thinking, is that it's not a bunch of library interfaces for parallelism. Okay, so it's not the OpenMP interface for parallelism, or I don't know, the Silk++ syntax for writing a parallel program. That's not what parallelism is. It's not a bunch of libraries or interfaces, or the building blocks, the Intel building blocks. So it's really a set of core ideas, and what are those core ideas? And identifying those and educating our students, and I guess even people beyond being students, on what these core ideas are. And so part of it's just identifying what these are. Then I guess the other side of this is I think that if you really go back to the basics, that parallelism isn't that hard. And I'm going to put a little caveat on this on the next slide. But parallelism, where parallelism means making use of multiple processes, if done right, a lot of algorithms are natural parallel, but we just brainwash our students. Okay, at least at Carnegie Mellon we do, and I think most other universities are doing, into thinking sequentially, and we've been doing this for 40 years. And if we just sort of brought in parallelism at a much more fundamental level at an early part in the curricula, we could actually avoid this problem. Furthermore, that if done it right with appropriate and with people who have an appropriate knowledge of parallel programming, it's really not that hard, parallelism. At least certain aspects, and I'm going to put one caveat on the next slide here, which is this. I want to make a very clear distinction now between what I call parallelism and concurrency. And these particular terms don't matter that much. And I think Jim was at a workshop last summer where we spent hours fighting about if these are the right terms or not. But what I want to do is make a distinction between parallelism being a property of the machine, having multiple processes running to get speed, the only purpose of which is to get speed up, since you're now going to be loading, balancing the load across multiple processes, versus concurrency, which is it's a programming issue, where you've actually got multiple interleaved threads, and you're making use of these things which are running concurrently and non-deterministic interleavings. Okay? So, for example, most operating systems have always been concurrent. We've been teaching the bakery algorithms on locks for the last 40 years, and on machines which are completely sequential. And it's not because we want to speed things up. It's because we have a multi-threaded process. We've got multiple threads running, multiple processes running on a machine, a sequential machine. They're interleaved. And so these interleaved processes can interact with each other. And so we need locks and we need concurrency, right? And it's running on a single processor. So that sort of concurrency has existed for many years and is got nothing to do with parallelism. It has to do with interleaving of threads, nothing to do with hardware parallelism. Okay. Now we've got a sort of what I call deterministic parallelism, and I'm actually going to focus on this today, which is this idea that you can actually have a sequential semantics, okay, no non-determinism, and it be running in parallel. Okay, and I claim that this is actually the part that's not understood, that if you look at curriculum today, this is the part that's least understood. Like I said, we teach this. I went through our curricula, and we cover the bakery algorithm in 4 different courses. We cover interleaving of instructions in 3 different courses, in the OS course, in the distributed systems course, and in our introduction to system courses. This sort of stuff we don't cover anywhere. And then, of course, you can have both. You can have things which are concurrent, so that your environment might be non-determinate. You've got demands coming in on the fly. You have to process things, and you're also running it on parallel machines. But I want to make a clear distinction here between concurrency and parallelism. My claim actually is that the parallelism, especially this deterministic parallelism, is much easier than people think if you were just trained properly. And I just want to go through in this talk and give some examples of why I think this. Okay, so here I'm starting with quicksort. This is the code from a book, Algorithms in Java, by Robert Sedgwick. And it's a book that's used in a reasonable number of courses, introductory courses on data structures. And we can look at this, and it's what you might expect. It's got a while loop. It's got a couple more while loops in here. Okay, so this is clearly extremely sequential. It does some swap. So we pick a pivot. We find all the elements less and greater than that pivot and sort of swap between them. We do a final swap to put the pivot in the right place. And then we make a recursive call to quicksort, and then after that we make another recursive call to quicksort. Okay, so that's what you'd expect. So we teach this in this course as a sequential algorithm, and in fact this is extremely inherently sequential, this part here. And well, if you're a computer scientist and with experience, you'll probably realize that you can call these 2 things in parallel, but that's not how we teach it. We just say you call one and then you call the other. So that's an extremely sequential program. Here's actually, if we go back a few years, here's the exact same algorithm quicksort algorithm from A.O. Hopcroft and Ullman. This is a book from the 70s, an algorithm book from the 70s. And I actually claim, in some sense, this is a much better piece of code because this is at the right level of abstraction, is a parallel piece of code. So my point being here is that many algorithms are just inherently parallel. Okay, and if we just actually raise the level of abstraction, we would realize they're parallel. So in this case, there's a huge amount of parallelism in quicksort. There's the fact we can make the 2 recursive calls. And here it actually, what this says here is just how we put the results together. It doesn't say we have to call these sequentially. It doesn't say we first call quicksort and then the other one. It just says when we put things together, we first put these and we follow them by S2 and we follow them by the quicksort of S3. Furthermore, this here can be done in parallel, that we can actually, when we're picking the elements S1, all the elements less than the pivot, that can be done in parallel. We can compare our keys to the pivot in parallel, So we've got n, the inputs set here, it might be a size n. We've got n of those, and we can compare them all to the pivot in parallel. And then we can sort of collect them up. So there's actually a huge amount of parallelism here, and expressed at this level, it's actually, it's already in the code. And so if you go back in time, you actually find in the earlier books, they described the algorithms more in parallel than they do now. That over the years, we've gone into more and more sequential thinking. So I guess there's a couple observations here. One is that there's a lot of natural parallelism algorithms, and if we describe them at the right level of abstraction, we would notice that they're there. And furthermore, when we do describe them in courses, we really should point out that they're there. We should show the students that this is parallel. We should tell them that they can make the two recursive calls to quicksort in parallel. We should tell them they can compare the key to the pivots, to the pivot to the keys in parallel. And so that's sort of the lost opportunity. And so, so the point being that there's a lot of inherent parallelism. So actually, this is quicksort in a language that I had worked on back in the early 90s called Nestle. And so this is actually, I was motivated, the particular syntax is actually motivated by A.O. Hopcroft and Ullman's code. And so it's just sort of a set notation here that says pick all the elements less than the pivot. So this is the S here. For every element in S, it's, there's a set notation, pick the elements less than A, pick the ones equal to A, the ones greater than A. These are comprehensions. Various other languages, such as Haskell, have similar sorts of constructs. This was actually, the original motivation for this comes from Settle, which is a language from the 70s. And then it says call quicksort on the elements which are less. And so for each V in the elements less and greater, so S1 and S3, apply quicksort, and then you put together the results here. Okay, you extract the, the first element result returned here in the second, and put the S2 in between. The point is that in Nestle, wherever you see curly brackets, it means there's potential parallelism. So it means that you can do this in parallel. You can compare all the pivots, all the keys to the pivot in parallel. And it also says you can make the two recursive calls to quicksort in parallel. So this forms of what's called nested parallel, and the term Nestle comes from nested parallel. It turns out that Nestle is purely functional, and this actually allows you to get this deterministic parallel. You guarantee that there's not going to be any race conditions from the recursive calls to quicksort because it's purely functional. This is something presumably you could do with F#. And so, so this is actually, you guarantee that this is safe in the sense that you'll always get deterministic results however you execute it, whether you execute the first quicksort first, the second one first, or them both in parallel. Okay, so I want to go on and say, so this is supposed to express the parallelism at a very high level. We say that we can do the quicksort in parallels, and we can pick all the elements greater, equal, and less than the keys, each of those things in parallel. But the question is, how do we actually implement that parallel selection here? So it's actually not quite obvious that, yes, we can compare the keys, E and S, to the pivot in parallel, but then we have to somehow pack them down, right? We have to start with this array of keys. Let's say S is actually an array. And we have to pack them down into just the ones which are less than the pivot. So here, let's say the pivot is 4, so we've packed out the elements 2, 1, 0, 3, and 1. So the question is, how do we do this? And it actually turns out that this is a relatively straightforward thing to do, but it does require a little parallel thinking, is that we actually have to realize that this can be done. So here's what we do, is we pick out all the elements which are less than the pivot, which are the ones here, and we've got the zeros where it's not less than the pivot. Then what we do is we do a so-called parallel prefix, where everyone here gets the sum of everyone before. Okay, so this 1 is the sum of everyone before in this array here. So this 3 is the sum of those 3 elements. This 4 is the sum of those 4, etc. So we've got this array of it's called the prefix sum, or the scan operation. And then what we do is we just write each element to the particular position if the flag is 1. So we write this, the 2 to location 0, the 1 to location 1, the 0 to location 2, the 3 to location 3, and the 4 to location, and the 1 to location 4. And that gives us the final result. Okay, so the interesting thing here is that now, unlike quicksort, which was just inherently parallel, it's not obvious that this is a parallel step, that it would seem completely sequential doing the prefix sum. Okay, so some of you have seen this before. I know many of you know this well. But there's actually a very easy parallel algorithm to do this. And this would be something that would be a core idea if you're going to be teaching parallel thinking. I think a lot of people we've taught in the last 10 years that have come out of Carnegie Mellon would be clueless on how to do this in parallel. Okay, and so, but it's actually a very easy idea. And in fact, it's a sort of a fundamental idea. And so I just want to go through it just to convince you it's doable for those of you who haven't seen it. So here's an array, and let's say I want to find the prefix sum with this. So we want basically the sum of everyone before it. So in this position, I'm going to want a 3. In that position, I'm going to want a 7, I guess. So how are we going to do this? We want to do it in parallel. Sequentially, of course, we just go through the array one by one, writing a loop and add it up. Well, it turns out that it's very easy to do this in a recursive way. What we do is we pairwise add these up. The 2 and the 1 becomes 3, the 4 and the 2 becomes 6, etc. Okay. And now let's say I just recursively apply a prefix sum on that array. Okay, so it should be clear I can do this pairwise adding in parallel, right? So that's easy to do in parallel. I make a recursive call, which is, of course, like as I mentioned, one of our tools of computational thinking, of recursion. So now I've just got the result of the prefix sum on that array, 0, 3, 9, 13. Okay, and some of you might recognize that if you calculate this in your head, the actual prefix sum, that these are basically every other result. That the prefix sum at this position is 0, the prefix sum at that position is 3, the prefix sum at that position is 9, and the prefix sum at that position is 13. So we've got half of our answers already by just basically adding pairs up, doing recursive call to prefix sum. And furthermore, if we've got half of our answers, well, if I look at the answer at any position, I can easily calculate the answer at the next position by just adding the key. So if I know, for example, at this position that it's 9, and I ask, well, what's it at the next position? Well, it's 9 plus 3, because that's the definition of prefix sum. It's just the sum before it, right? So we've got a simple way. What we do is we calculate, we take these elements and we add the element before it. So 0 to 2, 3 to 4, 9 to 3, 13 and 5. They give us these things, then we just interleave those. Oops. And that's our prefix sum. So what I'm saying, this is a very easy algorithm to describe. It's as easy or much easier than most of the algorithms we describe in an introduction data course. And it is a fundamental operation in parallel computing. This sort of stuff gets done all the time. But yet, I would say most of our students, if you gave them this on an exit exam as they leave the university, wouldn't know how to do it. Okay, even though I was able to describe it in a few minutes. And this sort of idea actually gets used. You can do a lot more than just prefix sums here. You can actually calculate the states of if you have a state machine and it's transitioning states with a bunch of inputs, you can calculate that using this. There's all sorts of things which normally you would think as being sequential, but are actually parallel. Okay, so here's actually the Nestle code for it. It doesn't really matter. You might not like the syntax, or you might, but it's basically saying this adds up those, pairwise adds up the elements, this is the recursive call, and this basically calculates the result of this plus some subset of the elements, and then you interleave it together. You get what you want here. So it's only a few lines of code. It's not a complicated idea. It's something that I think every undergraduate should know their freshman year. It's a core idea. It's not what's the syntax for OpenMP and nested loops? Okay, I'm a little worried that it's more likely our undergraduates know that than it is that they know this basic algorithm. Okay, so a couple observations here. One is that just because it seems sequential doesn't mean it is, that there might be a simple parallel algorithm for it. That this is actually a very common theme that comes up in the design of parallel algorithms is that if you can somehow reduce the problem to a smaller problem, solve it on the smaller problem recursively, and use that to solve the big one, that's very helpful. So this is not exactly divide and conquer. Divide and conquer, we solve two smaller problems, or two or more smaller problems and put them together. Here I'm just solving one. I only made one recursive call to the plus scan. I didn't do multiple. So it's not divide and conquer, but it's this idea of solving a smaller problem and using it to solve a bigger. This comes up a lot, I'd say a lot more in parallel algorithms and thinking about problems in parallel than it does sequentially. Because sequentially, you're often thinking of going through this loop one at a time, especially if you think about the scan, or you think about basically just starting at the beginning, going to the end. That when you want to think in parallel, you should be thinking, well, how do I take this really big problem, make it into something smaller, solve that thing smaller, and then help me solve the big one. That's typically more useful in parallelism than the one at a time approach, obviously. This last thing is that this is the generalization of the plus scan is basically you can generalize it to be a bunch of state transitions, and really what this is a special case of composing state transitions. In fact, Guy Steele gives a very nice talk on his version of parallel thinking, and he really emphasizes this idea that basically you can compose states. Mm-hmm.
Even the algorithm you described has some sequential components, right? I do this, then I do this.
That's right.
Then I do. So is there a notion of optimal parallelism that for an algorithm you cannot parallelize this more than?
Yeah, there is a lot of theory in the parallel algorithms about optimality and certain things you can't do better than. So in fact, you cannot do better than logarithmic depth for a scan because you basically have to do a tree. You have to pairwise add things up. And so the best you can possibly do is logarithmic depth, right? So yes, there is a nice theory. And in fact, this algorithm I described is optimal in that sense, that you can't do better. Well, I guess this is just, you can write quicksort in lots of different languages. This is quicksort in parallel in C++. The point is that the parallelism structure is the same in all these languages. We should emphasize the particular constructs. I think there's a lot of emphasis recently in parallelism on just looking at what the OpenMP constructs are, what the C++ constructs are, what foobar's construct, without thinking, well, what's the high-level idea here? One thing I should point out is that I mentioned that there's two types of parallelism, right? There's a parallelism from making parallel calls, that we can make the two recursive calls to quicksort in parallel, and then there's parallelism from the actual partitioning, which was what we did with the scan operation, the plus scan. We did the packing of the keys in parallel by doing that plus scan. It turns out that if you just take advantage of the recursive calls, and if you go to, there's a bunch, you'll find parallel quicksorts all over the place. It's in the set of examples in C++, it's in the set of examples of the threading building blocks, it's in a bunch of different ones. They all do the partition sequentially. There's actually very limited parallelism because you basically have to do linear work to do the partitioning. Then you can make two parallel recursive calls. So at the best you can do is it's still going to take you order n time. However many processes you have, the very first partition is done sequentially, and so it's sort of an Amdahl law, is we can't do better than that. And in fact, a nice way to look at this is if you look at the span and the sort of the critical path of dependencies in this computation, it's going to be order n. The total work, the total number of comparisons I do is n log n. And so actually the very best I can do is sort of dividing n by log n over n. That gives me sort of the amount of processes that I can make use of. So I can really make use of log n processes. So on the second slide I showed that curve of the multicore. Where we're at now, this is perfectly adequate. We've got 8 cores. If we're sorting a million things, log n is 20. We would be perfectly happy with this. If you go to 2015, that was 100 cores. This is not going to do. Okay, so this will work up to 10, 20. It's not going to go beyond there. Now, you could say, well, what if we did the other thing and we only took advantage of parallelism from sub-selecting the keys greater, equal, and less than pivot? And I actually took this piece of quicksort code off of the web somewhere. It was an example. I might have typed it in wrong, but of high-performance Fortran is some parallel language that was developed in the early 90s. It allows you to do this is the pack operation. It's the thing that packs all the elements less than the pivot. So inside of the pack, there's this prefix sum or the scan operation. And so here we're picking the elements less than the pivot, greater than the pivot. I guess here we don't do the equal ones, but We call 2 recursive quicksorts, and I guess this is an in-place version, so it just leaves them somewhere. And the point is, if these 2 are done sequentially, the recursive calls, but picking out the elements is done in parallel. And we can look at what the span, sort of the critical path on this is. Okay? Because the recursive calls are done sequentially, there's going to be a total of a linear number. The tree depth of these recursive calls is, the size, number of leaves in the tree is basically 1 per key. So there's actually going to be n total function calls made to quicksort. Okay? And if they're done sequentially, then it's going to take at least n time. In fact, it takes exactly n time if you do the analysis. But you get actually the same span as before. So again, if you look at the parallelism, we've got about log n parallelism. And it's not very much, and we could make use of this on maybe 8 cores and not many more. Okay. On the other hand, if you take advantage of both forms of parallelism, okay, the parallel function calls and also the parallel partitioning or basic subselection of the keys less than, equal, and greater than the pivot, you actually get a lot of parallelism, because what you can do is now this block is supposed to represent sort of the parallel work. It's sort of log n span for here to do the scan operation. So if we looked at the scan, it made a bunch of recursive calls. Each were half as big. So the total depth there was log n. And so it takes log n sort of span. The critical path is log n here. And then what you can do is you can say there's about log n depth to recursion here. You can prove that for quicksort. It's about log n deep in the recursion. It's approximately balanced in expectation. And so the total work is still n log n, but now this span, the critical path through the computation, is log squared n. And now if you look at the parallelism, it's the work divided by the span. We can make use of basically n over log n processes. So there's a huge amount of parallelism. If we have 1 million, we're talking about 50,000-fold parallelism here. So here we've got a good parallelism. Okay. But I guess what's important here is that we have to have a way to think about this. We have to have a way to analyze it. So as a person who's designing a parallel algorithm, and I want to compare 2 algorithms, like I want to decide whether it's useful to have the first form of parallelism, the recursive calls, the second form where I do the subselection, or both, or how useful it is to have them. I need a way to think about this. I need a way to analyze it, and I need a way to compare it. So again, this is part of the computational thinking. Is what Nestle does actually is it gives you actually a cost model, which allows you to calculate the work of a computation. Is if you make a bunch of parallel calls, like let's say if these were 2 calls to quicksort here, the work is just the sum of the 2. That's what it would take. Basically, it's exactly the sequential time. If I make 2 calls sequentially, it's the total time is the sum of them. If I make 2 parallel calls, the total work is the sum. I take the work from one call and the work from the second. They're running in parallel, but I still have to add the work. The span of them is the maximum. So if I make 2 parallel calls, I have to wait for the longer of the 2. So I take the maximum of those 2 spans. Okay, and so I can calculate the span. In fact, if you do this formally for quicksort, you get exactly what I had on the previous slide. You get a span of log squared n and a work of order n log n. So this gives you a formal way to determine what the work and span are. And then you might say, well, why is that useful? And well, it turns out that if you know the work and span, it's actually very useful about telling you how fast it will run on any given number of processes. Okay, now there's certain assumptions here that about locality and caches and stuff, which I'll get back to. But if you have a so-called greedy schedule, so it's the quicksort with all these recursive calls, you basically got a whole lot of parallelism. I have to schedule that parallelism onto my processes. I didn't talk about that. The point is that can be done by a scheduler under the hood. In fact, most systems, parallel systems like OpenMP, have a built-in scheduler under the hood nowadays. Some are better than others. In fact, the only decent one I've seen is the Silk++ one. So if you have a so-called greedy schedule, then you can show that the time is always going to be the work divided by the processes plus the depth. So if I know this work and I know the depth, I know quite a bit about the time. You can also show that the time is going to be at least the maximum of these 2. And if you think about it, the difference between the sum and the maximum is not that much difference. The most it could be is 2 if these 2 terms are equal. And if they're not equal, it's going to be less than 2. Okay, well, this argument is very easy. Why is the time at least the maximum? Well, if I've got so much work to do and I've got so many processes, the best I can do is evenly load balance that work across the processes. So it's going to take me at least the work divided by the processes. That's assuming I perfectly load balance it. And it's assuming that I can't get super linear speed up because of cache effects or something. Okay. Then there's the depth. Well, the depth is this sort of critical path that's saying if I take the longest path through my computation of dependencies, this is this is, or the span, I should say. D is a span. So it's going to take at least the span. So it's going to take the maximum of these two. And you can actually show that if you use a so-called greedy schedule, and a greedy schedule is just a scheduler that if there's work to be done, we'll do it. Just a normal notion of greedy. So, it tells me a lot about the time on a fixed number of processes. So that's just an argument why abstracting in terms of work and depth and span is good. Finally, if I divide, and I've been saying this along, if I divide the work by the span, it gives me a very good sense of what the parallelism is. Because it turns out when this thing is, when the parallelism, basically this tells me which of these two terms will dominate, right? If I have a P equals W over D, that many processes, then these terms are equal. I'd like the first term to dominate because then I'm so-called making good use of my processes. I've got so much work and I'm getting that work divided by P. So ideally, I always want this term to dominate, and the parallelism is exactly, when I've got P less than the parallelism, exactly when that term dominates.
So we're seeing a lot of new architectures that have sort of SIMD lanes, but with their own sort of program counters, like in GPUs. Mm-hmm. So in this case, within the SIMD lane, it might be better, especially for scan, to use a different algorithm, to not use one that's sort of this upsweep, downsweep phase, but more of like a hill of steel style algorithm within the SIMD lane, just because the constants involved are much less. And so even though the work is more, you'd be using that much work anyway. So is this...
No, I agree. All of these things are important, right? So I think the idea is that what I'm saying now is this is the fundamental idea you teach a first-year student, that they have to understand the basic idea of a scan, right? And then, in our curriculum, for example, we have an introduction to data structure course as a freshman, and then as a sophomore, we have the systems course, and we say, well, actually, the real machines aren't RAMs. They have caches. They have these other effects. And that's the sort of thing you're saying, is a real machine isn't ideal, like I'm saying, and yes, there would be trade-offs, and these are the next level of things that should be taught, right? Okay, so and more generally, your comment about trade-offs between work come up in a lot of different places. That's true. So a few more observations. One is that it's often important to take advantage of both this data parallelism, which is subselecting the elements less and greater than the pivot. This is something that's easy to do on a GPU. And also function parallelism, which is these recursive calls to quicksort, which are actually a little bit more difficult to do on a GPU. But in order to get good speed up, you have to do both of those. The other is that it's important to have some way for the user to get some sense of the costs of to compare. So always when we do algorithms, we want users at a rough sense to be able to compare insertion sort with quicksort. One's n squared, one's n log n. It's not perfect because it doesn't take account of caches, and the work and depth that I was described is not perfect in the same sense. It doesn't take account of secondary things, but it gives you at least a high-level sense of how parallel this algorithm is. And I think it's very important to have people in general, programmers in general, to be able to quickly look at two algorithms and have a rough sense of how parallel one is versus the other, so they can sort of proceed from there. A topic I didn't really talk about, but there's a lot of different ways to schedule that parallelism, and there's actually been a lot of very nice work in the last 15 years on sort of scheduling parallelism. That's more of an advanced topic. Okay, I just wanted to go through just a few more quick examples here to show that it's relatively easy to think about parallelism. So this is a block matrix multiply, a recursive block matrix multiply. So in order to multiply two matrices A and B, it blocks them each into groups of 4 recursively, and it makes a bunch of recursive calls to matrix multiply on these smaller blocks. So I basically multiply, I guess, these two, this one with that one, this one with that one, add those together, and that gives me the upper left corner of my result. So there's actually 8 recursive calls here. And so if you analyze the work, you make 8 recursive calls, each of half as big. Each one takes n squared work to do that's for the matrix add here, because I have to add this result to there. There's n squared elements. The total work is n cubed, which is exactly what we'd expect sequential work to be. If you analyze the depth, all of these recursive calls can be done in parallel. Every single one of them, there's 8 recursive calls. They can all be done in parallel. So you're making, so if I take the maximum of 8 things, well, it's just one of them if they're all equal. And then it's order 1 depth is just because I can do all these additions, the matrix additions in constant depth. So the depth here is only log n. I've got a very shallow network here. So this is an extremely parallel algorithm. If I look at the parallelism, it's n cubed over log n. This is a 1,000 by 1,000 matrix. I can make use of millions of processes. Much more parallelism than I need. Now, you could argue there's too much parallelism, and then it's really up to the scheduler to figure out which part of that parallelism to take advantage of. You can do matrix inversion. This is the so-called Schur complement of doing a matrix inversion. You can do a block method for doing matrix inversion. If you do the recursion, you get n cubed here. What's interesting here is that there's actually dependence, that there are sequential instructions. Here in particular, you have to, there's an inversion here that you have to invert this D1 first before you can generate the S1. You have to do this inversion before you can do that inversion. And so there's a sequential dependence, and so that's why there's a 2 here. And then if you solve that, the actual span of this algorithm, the depth of the span, is order n instead of log n. Okay, but it's still extremely parallel. The parallelism here is work over depth is n squared. So I still can take advantage of n squared processes in sort of the best case. Okay, you can also do, I don't know, a Fourier transform. These, by the way, all the examples I'm showing now are standard sequential code that you might have seen in an algorithm course, and they didn't even tell you that they're parallel, but are just naturally parallel. All you have to do is analyze the depth. That's the examples I've shown, well, except for the scan example, these ones are all naturally parallel. So here's you just make 2 recursive calls to FF. This is a wave. This is actually the complete Nestle code for FFTs. You make 2 recursive calls to FFT. You do some parallel multiplies and adds in the middle here. The work is n log n, the standard work for FFT, fast Fourier transform, and the depth is actually very shallow. It's sort of log n here. So parallelism, you can take advantage of order n. This is actually similar to the quicksort code in style, in the sense that you've got sort of the function call parallelism by making 2 calls to FFT in parallel, and also the data parallelism, because this statement here is a data parallel statement over n elements. Okay, I wanted to show one more example that requires something that's not just reanalyzing sequential algorithms. This is more like the scan, where we actually have to rethink the algorithm a bit. We have to do a little bit of parallel thinking in order to do a merge here. Okay, so this code here is actually sequential code for merge. It happens to be ML code. It doesn't really matter what it is, but it's just a standard algorithm where you start at the beginning of 2 lists. These are linked lists in this case. And you look at the 2 elements, whichever one is less, you pull it off the front of the list, you go to the next one. You just go down the list. Okay, so that's a complete ML code for it. Until you get to the end of this is just the base case. When you get to the end of the list, you just return one of the other list. Okay, what about doing this in parallel? This is a very sequential thing. It's like the scan operation, which we would think about it very sequentially. The goal would be is if you're experienced in parallel thinking, you should just know the answer to this immediately. But I don't think, again, if we gave this quiz to most of our exiting students, they wouldn't know how to do merge in parallel. Okay. And I don't know what the experience of people in the room is, but I would say most of our exiting students. Well, it turns out they're actually very easy algorithms for doing merging in parallel. And everyone should understand these, and everyone should have been trained in these when they were undergraduates. Let me just start. I just want to, the algorithm I'm going to show, and there's different algorithms actually, but the one I'm going to show is based assuming that our inputs are balanced trees in order. So what my input's going to be is a tree with some key at the root, all the keys less than it on the left, and all the keys less than greater on the right. I'm going to take 2 of these trees, and I'm going to merge them. Okay, because the first thing you should notice is if I start out with a linked list, I'm never going to be able to do better than linear span, because I have to go to get the next element in the linked list. I'm going to have to basically follow that linked list. So the first thing you should say, well, if I start with a linked list, I'm screwed. So let me start with a tree. It turns out you could also there's versions to do it on an array. The particular version I'm going to do, it works on a tree. So I take two trees, which are both have the keys in order, and I'm going to merge those two. And here's just a simple, this is actually ML code again, a piece of code that given a key, a pivot here, and a tree, so the second argument is a tree, it's either an empty tree or it's a tree with a node in it, then you're basically going to go down and you're going to split it. You're going to follow down a bunch of nodes until you get to a leaf and break off the elements less than the pivot and the ones greater than the pivot. So this is basically splits into keys less than greater than the pivot. It's different than what we did in quicksort because our elements are already sorted. So this actually only takes logarithmic time to do this because I just go down the tree. So in logarithmic time, assuming this tree is balanced, I can split this tree into two because it's already sorted. I'm just going through. If this was an array, this would correspond to a binary search. So if you gave me a pivot in an array, in order to figure out where that pivot in the array is, I would do some binary search on it. And that's the array version of this algorithm. OK, so here, so basically the whole code for merging, that's 2/3 of it there. This is the rest of it. OK, I guess I'm missing the base case, actually. But I'm done now. Here's a parallel code, an extremely parallel piece of code for merging. OK, so let me just go through this. What I do is, like I said, I've started out with two trees, A and B. This is my tree A. That's my tree B. I assume they're both balanced. And I'm going to return a tree as output, which is itself also balanced. Now, how am I going to do that? I'm going to basically take my first tree, pull out the root. OK, so that's some element that's greater than all of these elements and less than all those elements. I'm going to now make a now I'm going to use that root to split the other tree, showing the code based on the code in the previous page. That gives me two trees, the ones less than the pivot and the ones greater out of B. And then I just recursively merge this AL with a BL, all the elements less than the pivot, the AR with a BR, all the elements greater than the pivot, and I'm done. And then I just put my pivot in the middle, or the thing I pulled out in the beginning. Okay, so that's a piece of code. Now you might say, well, I haven't analyzed this. Is this an efficient piece of code? If I wrote this sequentially, if I'd made these two recursive calls, so this is parallel now because I can make the two calls to merge in parallel. If I did it sequentially, or if I analyze the work, what is it? Well, it turns out that it is a, if I do the merging in parallel, the work is actually linear. You get a recurrence basically that says it's n over 2 times n over 2 plus log n, which is the time for doing the split. And that just solves to linear. OK, so this is a linear time algorithm. So if I ran it sequentially, at least big O is just as fast as the version that comes in from the head. Now, in practice, it's probably a factor of 2 slower because of various overheads of dealing with trees instead of lists, et cetera. But it's at least within a constant factor. So even if I did this sequentially, it would be reasonably good. If I analyze the depth, well, there's this log n partition time here for doing the split. And then I make the tree depth here of recursion is log n. So each node in my tree has log n span. The whole tree has log n levels. So the whole depth is the product of those two. It's log squared n. And this is just using those rules where I take the maximum of the span for these two recursive calls and then add in the span for that. And that gives me these bounds. So anyway, it's a reasonably simple piece of code. It fits in hardly any. I guess I cheated a little bit. I left the base case off of here. But it's not that much more complicated. And this is something everyone should understand. Again, if you want to write an optimal version, I'm sure you'd do something fancier. But at least at minimum, you should understand that this is a way to do merging. Now, it actually, just an interesting comment here. As it turns out, you can actually improve this span here from log squared n to log n using an interesting old concept from parallel computing called a future. And this is actually an advanced topic. I wouldn't actually teach this to a freshman, but it's sort of interesting to realize this, is that as I'm splitting this thing here, so I take my M and I split this, and I start splitting this, I can actually start feeding the results from my BR, BL, and BR to my recursive calls before they're even done. It gives you a sort of a pipelining effect. And you can do this with futures, and I think futures is something a few people in this room have worked with before, is you basically, all you do is when you call this split operation here is you wrap it in a future, and you actually have to, this is my recursive split. So whenever I do my recursive split, I wrap in a future. And what a future is, it's basically, it says, go off and do this computation, return me a handle immediately that I can pass around to other people. And when I want the actual value, I ask that handle for the value. And if it's ready, it gives it to you immediately. If it's not, then it basically waits until it's ready and then gives it to you and suspends you until it's ready. That's what a future is. And if you just map, in my split operation, you just wrap futures around those two calls and then use this. It turns out you can show that the whole depth here reduces to log n, the span. You actually get more parallelism. Now, to analyze this is more complicated, and again, I wouldn't leave this as the first thing you teach in parallelism, but it goes to show that you can then, you can have a formal way of sort of analyzing what a future will give you, that if I give this pipeline parallelism will give you. Okay, so more observations. One is divide and conquer is more useful, even more useful in parallel than sequential. So, of course, we've all been using divide and conquer and sequential algorithms forever. But when you did merging, you didn't use divide and conquer. You used something that started at the beginning of the list. Now I'm saying even for merging, and there's many other cases like this, even for many things that you haven't used divide and conquer for, now when you start thinking parallel and thinking about how to do these things in parallel, you should be thinking how to do it in divide and conquer. The other thing, trees are better than lists in parallelism. In fact, lists are a real drag, not a good data structure for parallelism. That if you start thinking in parallel, you basically are going to stop building data structure out of linked lists. You're going to build them out of trees, or arrays are okay. There's lots of things which are okay. Basically, you want something where you can access all the elements in the sort of, any element in some time that's less than the size of the data structure. If I have a linked list, I always have to go all the way down to the end of the list to access that last element. And the other sort of, this sort of advanced topic that sort of the tick means here is that pipelining can actually asymptotically improve the depth of this algorithm, the span of this algorithm. I should say span there. Okay, so the observations. So his sort of summary of what all the observations in the talk were. There was some general observation is that natural parallelism often too low level. Natural parallelism often lost in low-level implementations. So that was the quicksort example, where we should be teaching people that this is a parallel algorithm when we teach them quicksort, and we should do that from day one. And people should just understand that. And not just the two recursive calls are parallel, the fact we can pick the elements greater or equal and less than the pivot. There's a lot of lost opportunities in describing parallelism to our undergraduates, so in general. And another one is just it's lots of things which seem sequential are actually not that hard to parallelize. And there were two examples. One was merging, and the other was the scan operation. I think those were, I hope I convinced you that those were quite simple algorithms. I could write the pretty much complete code for it in 10, 15 lines, right? Some other model language issues, taking advantage of both data and function parallelism, the need for some abstract cost models so that at least you can get some grasp on the sort of parallelism that's available. And so we talk about work and span and how you can divide work by span, and it gives you a sense of the number of processes. And also work tells you whether it's going to be as efficient as the sequential algorithms in terms of the total work it does. There's lots, I didn't really talk about scheduling. And another comment is, I didn't really talk much about this except in one of those early slides, with that it's all the examples I've shown are deterministic parallel. However you schedule any one of those bits of code, throughout this talk, it wouldn't give you a different answer. There's no, a lot of complications people have with designing parallel code is, just debugging. If you get different answers each time you run it, these are non-determinists, it's going to give you a huge headache. Everything I've shown here will always return the same result. It's got a sequential semantics. And I think that's very important if all you're doing is designing an algorithm. Now, like I said, There's a lot of applications where you need the concurrency. In fact, there's a lot of applications which run on one processor where you need concurrency, like an operating system. So then we do have to understand interleaving and coherency protocols, et cetera. But if that's not what you're doing, if you're just designing an application to run in parallel, the application does not interact with the environment around you or interacts at a coarse level instead of at a very fine-grained level, then you should try to be deterministic. I talked a bunch of different algorithmic techniques. I talked about recursing on smaller problems. Right? You take a big problem, this is a scan, you solve a smaller scan and help you. This comes up over and over again. I didn't talk much about the transitions can be aggregated. I talked about divide and conquer, trees, and pipelining. There's actually, I teach a course in parallel algorithms, there's actually a bunch of other sort of core ideas in parallel thinking, which I didn't even get to today. There's ideas in graph contraction to design graph algorithms, identifying independent sets, which is useful in a bunch of different algorithms, some in computational geometry, like Delaunay triangulation, et cetera. Symmetry breaking. So these are some of the other sort of core ideas in parallel algorithms of thinking about solving parallel problems, deterministic parallel problems. Okay, so I'm short of time. I also had some slides on locality. I'll just quickly mention that one issue with everything I've talked about so far is I haven't talked about locality at all. And I think locality is actually a very interesting problem in parallel because, we're now sort of at least somewhat used to analyzing algorithms for caches sequentially. When you get to parallel computation, dealing with locality is a whole other bag of worms. But I actually think there's very nice ways of dealing with locality in an abstract way. In the same sense as what I've been showing is an abstract way to think about parallelism, there's an abstract way to think about locality where the locality is tied much more to the application, so properties of the application or the algorithm, than it is to a particular hardware. So that you can define locality in terms of properties, so I can come up with some measure of locality like we did for work and span, some measure of locality based just on the algorithm itself. And then this will help you map it onto a machine that has multiple levels of caches or has a local and non-local memory, et cetera. Okay, so to finish up on the idea of parallel thinking is I've really concentrated on just one piece of what I call parallel thinking, which is what I call the deterministic parallel algorithm. So just without having any concurrency. So there's no non-determinism in what I showed. I think it's still very important to do concurrency. So these are applications where there's just inherent non-determinism in the environment. You're getting requests online and you have to deal with them. So there's just inherent non-determinism. And so I think it's important to sort of identify, sort of like I've tried to go through in the case of the deterministic parallel algorithms, sort of what the core ideas are, at least what I think everyone should know about parallel thinking in that context. There's a similar set of ideas that you'd want to know about the concurrency context, and I've listed some of it here. And also similar sorts of ideas that you'd want to know in terms of architectures and cache coherency protocols, et cetera. Okay, so I guess what I've talked about today is actually based on 30 years of research by lots of different people. So a lot of the algorithms aren't my algorithms. And a lot of it's come out of the theory algorithms community and also the programming language community, although I've often twisted it a little bit. So my conclusions are educating, I guess, programmers for parallelism is key. And again, I think there's been much too much emphasis on teaching a particular parallel programming paradigm, OpenMP or some language for a CUDA, for example, for a graphics processor or whatever. And so you teach them, you give someone a book on this topic and they go off and they learn how to do it. But they don't understand the high-level concepts about parallelism. And I think there's too much emphasis, and I think it's very important. I also think it's very important for people to clearly separate what I've called parallelism and concurrency, and like I said, people have argued about whether these are the right terms, but clearly separating out when you're trying to take advantage of multiple processes in your hardware versus when your actual application has concurrency in it. There's actually, it's a real-time application. You're getting demands from the outside world, and you have to deal with those, and they're coming in a non-deterministic ordering. I guess another comment is that, I would actually say, this is more for me as at a university rather than being at a company at Microsoft, is that it's important to teach these ideas from day one. That when we first start teaching computing, our very first data structures course, our very first programming course, we should be teaching parallelism. In fact, both parallelism and concurrency should be taught from day one. I think concurrency is more difficult. I think it's a little bit more of an advanced topic. So probably only the most simplest things should be brought in concurrency, but I think some of it can be introduced from day one. And in fact, I know MIT now has an introductory course where they start introducing some concurrency from day one. Then I guess the last thing is, I've tried to go through what I think are some of the core ideas in parallel algorithms, deterministic parallel algorithms. I think it's actually reasonably important for the community to understand what the core ideas in all these different areas are, so that everyone is properly trained in how to think about parallel algorithms, how to think about concurrency, so that we can sort of move forward on making use of these parallel machines. Okay, so that's it. Questions? Mm-hmm.
Yeah. So how much of this depends on using a functional language?
Well, basically what the functional language does is it gives you guarantees that it's correct. If you don't use a functional language, then you either have to use a race detector, and that's the Silk approach, is that you run it in a C-like language, you run your race detector, it tells you if there's any races, and you run it. Typically, the race detector slows down the program by a factor of 10, so you can't have it running all the time, but you run it on some test data and hope that if you run it, it doesn't detect races on test data. So what the race detector does is it guarantees that when you make parallel calls, there's no races. And so if it passes the race detector, then it will be deterministic. And the other approach is just to cross your fingers, I guess.
So you talk about ideas or ideas for thinking about parallel algorithms and for how to present them to, say, undergrads. Mm-hmm. And sort of today, when we were talking about scan or matrix multiply and stuff, we sort of initially looked at sort of a PRAM model where we talked about actual data structures and how the computation is structured. Mm-hmm. And then we talked sort of what I would call like a model of circuit families, mm-hmm. where you showed the sort of data flow, mm-hmm. And how, I guess, that model of parallel thinking has size mm-hmm. and depth complexities, which you talked about in terms of span and work, but and futures can be represented in circuit families just sort of by the normal data flow, like we just have a wire coming down to the other part. So I was wondering, sort of the circuit family style of thinking or the data flow style of thinking about parallel algorithms is very nice because it's very visual, and you don't get lost into how do I map my trees into cells of memory or anything that's very sequential, because it's all connected by rubber bands that are the lines and stuff. So is the model of circuit families for parallel computation something that we should be teaching to undergrads, and then how you take that circuit and then schedule it onto real hardware or data flow computing? I mean, it sort of seems like it's a more intuitive way of thinking about it.
I mean, that's very much, I feel. So if you notice, I actually never used the term PRAM here until the very last slide. Because this isn't the PRAM model. The PRAM model, you assume you've got P processes and you do your own scheduling. This is a very different model. In fact, if you look at the merge code or the quicksort code, I mean, you don't see processes. In fact, if you noticed, you might not have noticed, when I did quicksort and analyze complexity, I didn't mention processes a single time. The term processor never showed up here. And I believe that's very important, that this piece of code is a parallel piece of code. It doesn't say anything about processes.
It also abstracts into data structures as opposed to indexes and arrays and stuff, which I thought was nice.
So I would say that's definitely the right approach, because it's more abstract. You can basically go through this code, you work out the work and the depth, and then on the very last step you can say, well, if I had P processes, how fast would that run?
So my question is should we be presenting data flow computing or circuit families to undergrads? Because you can show me this algorithm and I still don't really get it until I see your example for 8 or 16 or whatever in terms of visually showing the flow of computation on the screen. Exactly. So this is
Yeah, no, this is very much the, right. Yeah, so I would say it's this data flow style of programming, basically. Well, like I said, it really only comes down to two trivial ideas, which is that the work is, sorry for going through the slides. The work is just if you make two parallel calls. This is really everything. It's encapsulated. The whole thing is encapsulating in these two equations. Is the work is the sum of the recursive calls, and the span is the max. By the way, the term span was, I've always used depth instead of span in my work, and Charles Liserson in work on Silk has always used critical path. About 2 years ago, we got into a fist fight, and we agreed on using span as a compromise. But it's not a standard term for that. So some people use critical path, some people use work span, some people use depth.
But from a conceptual point of view, it's just that visually seeing that data flow graph really illustrates work as the number of boxes and span as, the depth or whatever.
Mm-hmm. Yeah, no, I think as well as showing the equations, it's very useful educationally to show these sorts of boxes. Yeah.
I just wanted to say as a practical thing to get programmers to do this, just based on my group's experience,
Mm-hmm.
the key thing was getting us out 8-core machines. And all of a sudden, it became worthwhile for us to put in the effort to learn to do the simple stuff. And if you're in a language that allows functional programming but doesn't require it, it motivated us to get rid of those side effects.
Yeah. I think this 8-core, I think there's going to be a huge jump that there's somehow 4 cores was not enough parallelism to motivate anything. Because most of what I showed today, if you actually code it up, you lose a factor of 2, 3, from just going to parallel algorithms. Like the scan is a good example. You lose a there's twice as many operations in the parallel scan as in the sequential scan. You just lose a factor of 2 off the bat. So if you've got 4 cores, you're not going to be satisfied. So I think you really need to be getting at minimum 8, and I think it'll be a huge difference when we get to 16, 32, 64. I think that's when people will suddenly get it. They'll say, wow, parallelism is useful. But somehow 4 is not enough because of the overhead of parallelism. You lose more than half of that just off the bat.
We need to get the people who are writing the tools in the libraries now to have those 8 cores so they're motivated to do it for themselves and not just for some abstract it would be good in the future.
Yeah. So it's true in the course I teach. I had a 4-core machine last year, and I had an 8-core machine this year. It made a difference. That people felt more satisfied getting a factor of 5 speed up as opposed to a factor of 2, 2.5 speed up.
Sort of play the devil's advocate here. You used the justification of Andrew Chan's comments about 100 processors. 2015, I think it was.
Yeah.
A lot of people don't believe that. In fact, it could stop as early as 8. If it does stop as early as 8, can we forget all this?
Well, it would become more of a niche field that people will still already have much bigger parallel machines. But if you don't have it on your laptop, then it wouldn't be something you'd use on your laptop. I mean,
This is really a hard sell, right? People have been saying for a long time that we should be teaching parallel thinking. And as you said, Carnegie Mellon doesn't do it very well yet.
Well, I mean, it is based a bit on this belief that we will have more than. I mean, like I say, 8 cores is sort of the elbow where it might become useful, right? 16, 30, but I think we only have to go up to 32 when it becomes clearly useful. 16, I think 8 and 16 are sort of like, well, it's quite a bit of work for this, and there's probably other ways I can take advantage of 8 cores, right? I think once you get to 32, I think you have to start thinking this way. And I personally, I'm not sure if we're going to have 100 cores in 2015. I'm not going to, certainly not wouldn't put a big bet on that. But I'm quite sure that we'll have 32 cores at least by 2015 and beyond there. I mean, maybe I've been misled by Intel, but I think so.
NVIDIA is already integrating GPUs on the Northbridge, right? So I mean, you have literally tens of thousands of logical processing elements that are now sharing the same physical address space. So scan and some of these other things for large data sets could now be used by the operating system.
Right.
Instead of having to farm it across PCI Express into a separate memory domain. So I think we already have that now. We have tens of thousands of, basically hiding it through latency hiding mechanisms. We have this bandwidth now for pushing instructions through that we didn't have before, all in the same physical memory. So.
Dave?
So, are we making a mistake by emphasizing communication costs as a first order concern, even to our introductory programs?
Yeah, that's why I brought up that locality issue at the end, is that I don't think you can forget about communication costs completely. I do actually think you could do it at the freshman level, but not even going to the sophomore level. I think you probably have to start talking about locality. So at the end, I had that couple slides on locality, but I think these are all. I think even sequential computing, it's questionable, right? There's 100-fold difference between a cache miss and a cache hit, right? A level 1 cache hit and a complete cache miss. And so even sequentially, but yet we still do teach quicksort, right, without worrying about the cache. It turns out quicksort is okay for cache locality because it scans the memory in order, right? So a lot of these algorithms are okay, and I guess my point is, in fact, a lot of the algorithms I showed are actually reasonably cache friendly. And it's the point being is that if we are going to talk about locality, we want to do it in a way that's not at a low level, like isn't talking about processes and communicating, that it somehow captures a property of the program. So recursive matrix multis has a huge amount of cache locality. It's hugely local. We all know matrix multiply is about the best possible thing you can do for a cache, right? And the reason is that if you look at all these cross terms here, they're all sharing the same matrices. They're just doing the same thing over and over again. So if we can somehow capture that at a high level as opposed to going to think, I think it'll be very helpful. Because otherwise, locality in parallel machines is a nightmare. It's, there's so many different ways that you have locality in parallel machines, and it's much more complicated than sequential.
What do you think is the future of transparent caching? I mean, as we scale up to 100, 12,000 nodes, I mean, for granularities like scan or matrix multiply, are we going to continue with the same sort of caching paradigm that we have for sequential? Or are we going to have to manually manage that as part of our algorithm design?
Well, I hope you wouldn't have to. Certainly, no one would want to manually manage a cache. I mean, it's hard enough sequentially to manually manage caches. That's why we went to automatic caching, and it would be much harder parallel. So, yeah, so I would certainly hope that it's done under the hood for you, ideally in hardware. I think cache coherency schemes. Now, whether you need the stricter schemes or you can get with relaxed, probably maybe you can get rid of relaxed if the system on top knows what to do with it. But I think we do need it to be automatic. It's my opinion. Yeah. Just one more.
One of the tricky things that we do get taught when we're sequential programming is how to do everything in place. And from the pictures of the algorithm which you showed, it seems to be less in place than the equivalent sequential algorithm. Is that a characteristic across the algorithms you've studied?
It is a characteristic. You often do lose, like I said, you sort of lose a factor of 2 on a lot of these algorithms out of the box. And for the quicksort, that in fact the factor of 2 comes from the fact that it's the parallel version where you do the subselection is not an in-place version, and that means you're going to touch twice as much memory probably, and that's going to give you a factor of 2, and it's not more than a factor of 2, but a lot of these cases, yes, it requires, because you're doing it in parallel, you have to do it in separate spaces. I mean, this is not a comment about quicksort in general, specifically, but in general, you often need to do it in separate spaces, and that means touching more memory.
Do you think that will inform the computer architecture? Like, is there something like is there something you thought of that could be done with the way things are cached to be more friendly to that pattern? Because the caches today are very friendly for this in-place sort of stuff.
It could be. I mean, if you think about functional languages, they don't do things in place, right? Because you're always copying to, unless you optimize, you're always copying to a new location. And there has been work that shows that the sort of caching schemes you would want in a functional language are different. So maybe the same sort of thought process would also say the same thing here.
Well, thank God.